Hi everyone. This video is going to be about two topics that are related to each other. They're called congruence and similarity. And they both kind of have to do with whether or not things are the same, but they're slightly different. So we'll start off by asking just a question to think about. Are these two triangles that I've drawn here, are those the same triangle? So obviously they're not exactly the same because I've taken this one and done a transform on it, right? I took my glide arrow and moved it over here. But they're still the same in some sense, right? All the sides are the same, all the angles are the same. This one's a 30 degree, 60 degree, 90 degree triangle. What if I do this? Now are they the same, right? Or I could ask this question, let's say I took that and did a, same triangle, but I did a glide reflection on it, right? Something like that. Are those two triangles the same? The answer to that is it kind of depends on what you mean by the same. So I'll ask one more to kind of show this point here. Let's say I've got this same triangle and shrink it down, scale it down that small. So are those two triangles the same? Well, the angles are the same, right? Same thing if I scale it all the way up, right? The angles are all going to be the same, so there's going to be some relationship between them. But this is kind of showing that we need some sort of way to talk about when the angles are the same, and then when the side lengths and all the angles are the same as well. So I'm going to start off with defining congruence here. So one way we can talk about things being the same is using congruence. So I could say two geometric figures are congruent if their corresponding side lengths and corresponding angles are all equal. So I'll go ahead and use a rotated triangle here to show that in fact, if I rotate this triangle around, and that's all I've done to it, these are still going to be congruent, right? This side length corresponds to this side length, this one to this one, this one to this one, and same with the angles, right? We've got these corresponding angles, and then we've got a right angle here. For triangles specifically, this applies to all geometric figures, so like pentagons, 12-gons, circles, things like that. Well, not circle, but any polygon or a Conway criterion shape maybe. So I'll make a similar but slightly modified statement, say two triangles are congruent if all three corresponding sides are the same length and all three corresponding angles are the same measure. So you can see what I've done up here is I've drawn two congruent triangles here. So I can say when we perform translations, rotations, or I'll do them in the same order, reflections, rotations, and glide reflections. We preserve the congruency. Right? Meaning if we do any of those four things, we're still going to get a congruent triangle, right? If we have all these pieces of information, right, all three corresponding sides, if we have all three side lengths and all three angles of two triangles being equal, I'm going to go with corresponding again. If we have all corresponding side lengths and all three corresponding angles of two triangles, we're guaranteed they're going to be congruent. All right, but we don't always need all six pieces of information. Sometimes all we need are three pieces of information to prove that two triangles are congruent. So I'm going to highlight some key words here. Three pieces of information is kind of what we're going to be talking about, but then another key piece of that is that we've got sometimes on here. Okay, so not all combinations of three pieces of information are going to help us prove that two triangles are congruent. Some of them will, some of them won't. So let's say some combinations of information will suffice to show congruency, but some will not. So just to head off some questions that people might have, if I've got, I'll explicitly talk about those six pieces of information and point out that these need to be in a particular order. So I'm going to call these A, B, C, and I'll call this D, E, and F. So in order, those six pieces of information are that angle A is equal to angle D, angle B is equal to angle E, angle C is equal to angle F, side length A is equal to the side length D, side length B is equal to side length E, and side length C is equal to side length F. So those are the 6 pieces of information, and just making sure we know that that tells us that we've got triangle ABC is congruent to triangle DEF. This symbol here, this equal sign with the tilde over it, this symbol means that those 2 triangles are congruent in that order of lettering. Okay, so let's talk about what combinations work and what won't. I'm going to break this down into 2 categories. We'll call these sufficient, or kind of the good category, and then we'll say not sufficient. And I'll put a line down the middle to talk about that. So if we have, for example, all 3 sides, right? Think about that triangle there. We've kind of got all 3 of these locked in place here, right? So I've got this side length, and this side length. And it doesn't matter if I rotate this or reflect it or whatever else, I'm still going to end up with a, as long as you have these, right, 3 side lengths all being set in stone, that's going to be enough to prove that 2 triangles are congruent, right? If you've got this side's equal to D, E, and F, right? All 3 sides locked into place, that's going to be enough. So the way that we do a shorthand for that is we say this is SSS, right? That tells us all 3 side lengths. An example of something that's not sufficient is kind of the counterpart to that. So I've got this angle here, this angle here, and this angle here. So if I've got those 3 angles there, I can make a congruent triangle with this, but I'll show you, right? Just because the angles are the same doesn't mean that we're going to have a congruent triangle, right? I can scale this up or down, and that's going to give us 2 triangles that are, all the angles are the same, but they're not going to be congruent to each other. So this is something different. We call this similar, but I'll go ahead and put that in the not sufficient category over here. Sorry about that. So not sufficient, we would say AAA, which is all 3 angles. I'm going to put a note here that we can scale this up and down. Okay. So all 3 sides will work, all 3 angles will not. Just get another one over in this sufficient category. We could do, let's do side angle side. So the order of these letters matters. It's not just 2 sides and an angle. So one example of this would be, let's say I've got this triangle here, and when I mark something in red, that's going to be demonstrating that that's sort of locked in place. So this is one of my sides, and here's another one of my sides. And then the fact that the A is in the middle of those two means that this angle is also locked in place. So really the only thing that can be changed about this are these things in green here, right? But if you picture sort of two, these red pieces here as being like two sticks, right? It doesn't matter how pliable this stuff in the green is, as long as you've got these two sticks sort of locked in place by this angle, there's only one triangle that you can get out of that. So for that reason, we would say that that is going to be sufficient. Okay. Next up, I'm going to do angle, angle, side. So I'm actually going to draw this horizontally so it fits a little better on here. So there's my side. There's my side, and there's my angle in between there. Okay. All right. Next one that I wanted to do was angle, angle, side. And angle, angle, side, I'll draw an example of what that might look like. So here's an angle locked in place. Here's an angle locked in place, and then because the side is outside of those two angles, we need to pick, I'll pick this side over here to demonstrate that. So everything else about that triangle is going to be potentially something that we can change. Right, so all of this could be changing potentially. And this one starts to make a little more sense why this is sufficient when you think about this fact. So these two angles, this one here and this one here, are locked in place. Let's say that's 40 degrees and 40 degrees, right? Since we're looking at a triangle, if this is 40 degrees and this is 40 degrees, we know that this has to be 100 degrees, right? There's no getting around it. So really, if we have two angles, that kind of means that we get this third one for free, right? That third angle is locked in place. So now the situation that we've got is we've got three angles. And then the problem is that we could scale that up or down, right? If we only had the three angles, we could scale this up or down. But this side length here, that's sort of locking it in place, right? So if we have two angles and a side, that really means we have all three angles. This side keeps the scale of that object locked in place. So angle, angle, side, that will be enough for us. Another one that will work is going to be angle, side, angle. All right. So I like to draw this one with my side down here. So we've got one side, and then that order, angle, side, angle, means we should be looking at one angle on this side and one angle on this side. All right, so everything else can potentially change. All right, this angle could change. This side length could change. This side length could change. I sort of think about this one as being like you've got two telescopes, right? All right, you've got two telescopes, some fixed distance apart, and they're looking at a particular angle, right, up into the sky. So here they are on the ground, right? Some fixed distance apart. And if I point both of them at a very specific angle in 2D space, at some point they're going to converge at the same point on here, right? So there's really no way to change where those two are going to intersect if they're some distance apart and they go up top there. We actually saw this in our, we had our bank and our crematorium and our aquarium, right? They had some angles of elevation that we wanted to look up at our new building. So that problem, we were able to solve that because we have this relationship, right? This information is enough to tell us what's going on in there. So angle, side angle is going to be enough information for us. Okay. One that will not work is, so I'll put that up here. That's going to be side angles, or side angle, rather. The order of these letters, you can rearrange them however you want. If you arrange it in a certain way, as long as those two sides are together, you can kind of help yourself remember that this one, right, is not sufficient, that this doesn't work. But side angle, I'll do this with a really, obtuse, we'll do this with a really obtuse triangle here. So let's say that this side is locked in place, and then we've got a side next to it. So I'll choose this one over here. So I've got a side, and then the angle needs to be not in between those two sides. So not this one, but this one over here will work. Okay, so I've got side, and then angle. Okay, everything else can change about it. So if you haven't seen this before, this may look like a triangle that really can't change. It looks pretty similar to these other ones over here. But the trick with this one is we can take that side on the right. So I'll go ahead and copy that. Paste this over here. So keeping this angle the same, should move both these up here. So keeping this angle exactly the same on the left here. I can stretch this out, so I'm just going to stretch that right side. If you picture that as being like a stick, right? That's kind of centered on here. I can stretch that rubber band out and get another side. Right? It's going to stretch all the way out to that same spot. Same distance. Over here. Right? Maybe exaggerate that a little more. But you can see this distance here is the same as this distance here. So I haven't violated any of the rules about distances. But I've still got this side, and this angle are still locked in place. But I have two, right, no longer congruent triangles. So in summary, for talking about congruency, here we've got two categories. This combination of three pieces of information, any of these are all going to be sufficient, and any of these are going to be not sufficient. The type of question that I might, so we'll say, right, these are not congruent to each other. The type of question that I might ask about this is I might give you two triangles. So I might say something like ABC and DEF. And say, hey, if I tell you that angle A is equal to angle D and angle B is equal to angle E and side length C is equal to side length F, is that enough for these two triangles to be congruent? Is that enough information? So it'll be up to you to kind of take this information and say, okay, I've got angle A, and that does correspond with D, right? Assuming that it's the same as the last example where ABC is congruent to DEF. So it's going to be up to you to say, okay, A goes with D, B goes with, that should be an E, and C goes with F, so that's the right order of letters at least. So I've got angle A, and then angle B, and then side length C, so that's going to be, if this is uppercase C, this is lowercase c. So is that enough information, these three pieces? Is that going to be enough to prove congruence? Well, we've got a side length with two angles on either side, so that's going to be angle side angle, and that's going to be enough. So those will be the kind of questions that I'll ask about that. But yeah, just a matter of memorizing which ones are sufficient and which ones are not sufficient. I think if you kind of understand what I said during the explanation for these, then you shouldn't have to memorize them. You kind of just intuitively use them. Okay, so that's all I have to say about congruence. Another topic I wanted to at least introduce to you today is this idea of similarity. So we could say, I'll just write the definition right away. So we'll say two triangles are similar if their corresponding angles are the same measure. So we'll say all three. Same measure, equal, all right, these are interchangeable terms. You can think of these triangles as being scaled up or down. Okay. Here's an example of that. Right. Here's a triangle. If I take that same triangle and scale it down, we'd say this triangle is this triangle is similar to this triangle over here. Let's make that look a little nicer. Right. And just for good measure, I'm going to mark these angles as being the same, right? So this angle is equal to this angle, is equal to this angle, and then we've got a right angle there. Okay, so there's some special relationships that we can have between similar triangles. So I'm going to go ahead and copy this over here, and I'm going to label some angles here, or some side links here. So I'm going to call this one A, B, and C, and I'll call this D, E, and F. So some nice relationships between similar triangles have to do with their ratios. So an example of this would be that A corresponds with a D over here. This long side here, the hypotenuse, right, over A has some ratio to it, right? So we could say something like C over A. That ratio, right, maybe this is, 8 over 4, is going to be equal to 6 over 3, right, this ratio over here. So we can think of this as being like longest side over shortest side is going to be the same ratio for two similar triangles over here, right? Another way to think about this, so that may make sense to you. Another way to think about this would be within or between two triangles, right? If I say something like C over F, right? So this is long side over long side is going to be equal to short side over short side. So A over D, right? So these two are equivalent statements, right? If you look at the algebra of these, I can rearrange these letters and I would get the same thing over here. So just kind of pick one of these two ways of thinking about it, and that'll be enough to think about how to solve these. So you can probably guess the kind of questions that I'm going to ask. I'll give you, something like this is 8, this is 4, this is 6, and this is X. Okay. So that's just going to involve you figuring out, 8 over 4 is equal to 6 over, that's going to be 3. Okay. One other way that this shows up with similar triangles here is when they're on top of each other. So similar triangles sometimes overlap with each other. So you'll see, just to show that two triangles share an angle, sometimes you'll see something like this. Doesn't have to be a right triangle, by the way. I'm just showing that's just kind of how they happen to show up here. But let's say I take this triangle and I just scale it down quite a bit. So I've got this small triangle sort of overlapping on top of this larger triangle here. I can look at this triangle here. That is a triangle. I can mark this angle and this angle over here. And that's going to be the same as this larger triangle. Right, as long as this angle and this angle are the same, or we're told that these are, right, we're told that these are similar triangles, then we can start to do the same sort of ratios on here. So as an example, let's say that I told you that this side length is 2, well, let's say I told you that this side length here is 2 from here to here. Let's say that's what we're trying to solve for. All right, let's say that's x. And then everything from here to here is 7. And then let's say this is 5 over here. Okay, so that's all my side lengths marked here. I'm just going to draw this a little nicer. That's 2. That's 5. So setting up a problem like this, I can think about setting it up that first way where I compare within a triangle. So for the small triangle, we've got x over 2, and that sort of represents this medium side over the short side. So the short side over here, this would definitely be 5, but that medium side is going to be this whole thing over here on my larger triangle. So that's going to look like x plus 7. Okay. So that's one way to think about this, and I'll go ahead and solve for that in a second here, but just to show you the other version of this, if you wanted to compare, we've got x plus 7 over, so this is medium side over medium side, so that's going to look like x is equal to 5 over 2. So whichever way you want to solve for this, you're going to get the same answer for x. So let me just show you, this side over here. I like this one a little better. So algebraically, I know some people like to do the cross multiplication, but I'm going to show each step individually. So first thing I want to do is multiply, or I'm gonna split this up actually. So this is the same as x over 2, and this is equal to x over 5 plus 7 over 5. Okay. And then if I subtract x over 5, I get x over 2 minus x over 5 is equal to 7 over 5. I'm actually going to zoom in a little bit. Okay, so same thing, x over 2 7/5. I can take an x out of this, so this will be 1/2 minus 1/5 is equal to 7/5. I need a common denominator here of tenths, so I'm going to take all these fractions and turn them into being in terms of 10. So 1/2 is 5 over 10. 1/5 is 2 over 10. And then this is 14 over 10. So this is going to be x. X times 3/10 is equal to 14 over 10. So last step is going to be multiplying both sides by 10 over 3. So if I cancel out those 10s, x is going to be equal to 14 over 3. Okay, I know that most people prefer to do cross multiplication, so I'm going to show that method here. So cross multiplication says that if you've got two fractions equal to each other, this times this is going to be equal to this times this. So you multiply the cross terms and set them equal to each other, making sure that you're multiplying this whole thing here. So when we cross multiply, we get x plus 7 times 2 is equal to 5 times x. This is 2x plus 14 is equal to 5x. If I subtract 2x from both sides, I get 14 is equal to 3x. So dividing by 3 gives me x is equal to 14 divided by 3. Or I guess I can keep it in the same order here. 14 divided by 3 is equal to x. So we do get the same thing. Either setup, either method we want to use, just as long as you're able to solve for x, you should be in good shape. One more setup that I want to go over kind of separately, because it's got a lot going on in the problem, is a situation where we've got a right triangle. So of course when I try to draw a right triangle, I can't. There we go. We have a special case. When we drop an altitude, along a right triangle. That makes similar triangles. Okay, so let's talk about those. So here's my altitude. Again, this is the right angle. So when I drop that altitude line right from the orthocenter, let's say that this is 30 degrees over here. If this is a right angle, that means this has to be 60 degrees. This altitude tells us that this has to be 90 degrees. So if you think about it, 30, 90, and then if we're just looking at this left part of the triangle here, we've got a 30, 90, and then a 60 degree triangle. over here. This one on the left is going to be a 60, then 90 degrees, then a 30 degrees up here, right? Makes sense because 60 plus 30 has to be equal to 90. So what we end up with is actually 3 similar triangles. Right. So I'll kind of label them one at a time. Right, we've got this one is similar to this one, and that in turn is similar to the whole thing. All right. So 3 similar triangles. Just based on how complicated this one gets, when we just have 2 similar triangles, you can kind of see that it's going to be quite a bit of work to figure out some missing pieces along here. So what I'm going to do is just give you a example to think about, and then I'll talk about my technique for solving it. So we'll do that on either Thursday or the following Monday. So an example for you to think about. We've got right triangle here, and let's say this is 3, this is 7, and I'm looking for x. Okay. So you can kind of compare this to our aquarium and bank and crematorium type of problem. Very little information, right? Just 2 sides of this right triangle. But we can figure out this altitude pretty easily. Okay, that's all I wanted to say for this time. Hopefully this was helpful, and I will see you in class very soon.